I'm going to start with something that might not seem like it's connected to quantum physics, and that is light. And we start with the history. And what I mean by the history of light is our theory, our understanding of what light actually is and how we describe it. It starts in the 1600s with Isaac Newton. It was known that certain phenomena were associated or connected to waves. For example, reflection, refraction, interference, and diffraction. Now, these effects are connected to waves. And what we mean by that is that when we look at these four effects, in order to explain those effects, we have to assume that the thing that we're looking at is a wave. If we don't, we can't really explain them. Now, I accept the fact that when I say that, that sounds a little bit strange. For example, if we talk about reflection, if I take a tennis ball and I throw it against a wall, it will reflect off the wall or it will bounce back. The tennis ball is definitely not a wave. It's, if you like, a particle. For sure, that kind of reflection is not connected to a wave. But when a wave, like a sound wave, reflects off a wall or ripples on the surface of a liquid, bounce off the edge of the container, that's a reflection. In order to explain that reflection, we have to assume an understanding of what a wave is and how it functions. And if we don't, we can't explain it. These effects are so intimately tied to what a wave is that they are actually called wave effects. So when we talk about wave effects, what we mean is there is some process happening that I can only explain it on the assumption that the phenomena that I'm looking at is associated with a wave. Another way of saying the same thing, if you're looking at something and you can see that this phenomena, this effect, whatever it is, shows reflection or refraction or interference or diffraction, it is a wave effect. You have to use waves to explain it. Now, Isaac Newton knew about this because of water ripples and sound, although sound is not a visible effect, it's an audible effect, but water ripples are visible effects. And you can see reflection, you can see refraction, interference and diffraction from water effects. Now, it's nice if you know what these effects are. Reflection is when energy bounces off a boundary between one material and another. Refraction is where the wave moves from one material into another and it changes direction as a result of it. Interference is where you have two or more waves and they overlap. And if those waves are of the same type, so they're both, let's say, electromagnetic, or they're both sound waves, or they're both water surface ripple waves, then they will basically interfere with each other. And interference is a very simple process. They just add up. And diffraction is the spreading out of a wave when it moves past an edge or through a gap. And to show you what I mean for water ripples, I'm just going to pull up an image which I'm going to put on the screen. You can see the waves in the sort of, this is not quite the open sea, but in the sea here coming in. They've tried to show the ripples with these lines that they've drawn on top. And then what happens is when they go through this gap between this island and this island, they become curved. They don't travel in a straight line. You can see here, waves coming in and spreading out. You can see there's like a cone associated with the wave effect. Okay, now, Isaac Newton was aware that these effects, reflection, refraction, interference, and diffraction, they occur for water ripples, which are definitely waves. And he was also aware that these effects occur for light. Therefore, light is a wave. The next part of the story about the history of light takes 200 years, and really the late 1800s, with a guy named Maxwell. Now, James Clerk Maxwell was a genius, and there are various programs that are worth watching that sort of talk about him. And one of the links is here for a BBC program that discusses James Clerk Maxwell, which is worth seeing. Maxwell basically said that light is an electromagnetic wave. So Newton said it was a wave. Maxwell said it was an electromagnetic wave. We can draw a picture of this. This picture is probably my second favorite image in physics. Now, to try and make some sense of this, because it's basically a 3D diagram. The green wave is supposed to be going up and down, up and down. And the blue wave is going in and out and in and out. This is a 3D diagram. It doesn't really matter which one is which. If I say that the blue one is E for the electric field, and the green one is B, which is the symbol for a magnetic field. An electromagnetic wave is an electric field and a magnetic field that are perpendicular and they are in phase. Perpendicular means they're at right angles to each other, and in phase means that their peaks and their troughs and their zeros are occurring at the same time. Now, we don't have to delve into Maxwell's theory of electromagnetism, but at the time, Maxwell's theory of electromagnetism was considered the ultimate achievement of physics. It was basically said that there are two peaks of achievement for mankind: Newton's theory of gravitation and Maxwell's theory of electromagnetism. And between them, those two theories basically explain everything. The suggestion was that at that time, physicists had basically solved everything to do with the universe. It was a bit of a moment, not going to lie. It was madness to say that sort of thing. Every time you get a little bit too cocky and you say stupid things like that, like we've solved it all, we know it all, nature will turn around and bite you. And that's what happened. One of the things that was stated was that we now basically know everything. And there are one or two small issues that we haven't quite sorted yet. But we'll get there. We just haven't quite worked them out yet. One of those problems was something called the photoelectric effect. The photoelectric effect, bizarrely for physicists, is actually one of the most well-named effects in physics. Photo is a reference to light going in. Electric is a reference to electrons coming off. We shine light. In this case, it was UV onto a metal plate. In this case, it was zinc, and we produce sparks. Now, this was carried out in 1887/88 by Hertz, as in the unit of frequency of a wave. And it was a very simple process. And the idea is that you have a plate of zinc, you shine ultraviolet light onto it, and electrons jump out. The photoelectric effect. This effect, by the 1900s, has not been explained. This effect was one of those small problems that was referred to that we can't quite explain it yet, but, we'll get there. Okay, so let's look at why this effect was a problem. At this time, the model of light was the wave model. It was known that waves contain energy. In fact, we often talk about the energy of a wave as being proportional to the amplitude squared in physics, and we normally just state it and hope that the students will remember. We don't normally discuss why it's proportional to the amplitude squared, and we also don't normally talk about why are we using a proportionality and why are we not writing an equal. And the answers to that are twofold. One, it's ever so slightly complicated to show that the energy of a wave is amplitude squared. It's not a big problem though, and I'll probably do that in a different video and make that available. But the reason we use a proportionality rather than an equal sign is because when we write an equal sign, it depends very much on what type of wave it is, on what the shape of the wave is. And different shaped waves, of which there are lots of different shapes, they have a slightly different equation. But common to them all, no matter what the shape of the wave, is that they all depend on the amplitude squared. So that's why we talk about it like this. So that made the photoelectric effect very simple to explain. Waves fall onto the metal. The electrons use the energy of the wave. And that was basically the wave explanation of the photoelectric effect. Very, very simple. And everybody was kind of fine with that because we all know that waves do contain energy. If you have any doubt about that, then next time you're at the sea, just stand in the water and feel the waves as they move past you, because they'll push you and pull you. And also, if you want a different idea about the energy of a wave, in summer, wear a black t-shirt and stand in the sun, and you will feel very quickly the effect of waves containing energy, because you will get very hot very quickly. So let's look at some of the other observations of the photoelectric effect. So when this experiment was actually carried out, what did people observe? So observations. Okay, number one, UV leads to electrons. And we've already seen how the wave model explains that. Waves have energy, falls onto the metal, electrons make use of the energy somehow, and they're emitted. 2. If the intensity of the light increases, we see more electrons. Number 3. If the frequency of the light is below a specific value, which is called the cutoff frequency, then no electrons are seen, no matter how intense. You can make the light mega, mega, mega intense, but there was no electrons coming off. 4. Time taken for the light to produce electrons was almost zero, in other words, instantaneous, and did not change with light intensity. Okay, and there are other observations, but we'll kind of stop there. Now, observation number 1, as we said, was simple. Waves have energy, and electrons, that's going to be my shorthand for electrons. Electrons use the energy to escape. Number 2, if the intensity of the light increases, we see more electrons. The way we explain this is very simple. If intensity increases, the wave has more energy. Therefore, we get more electrons. Pretty simple. How would we actually explain that? Well, if a wave looked like this, if you made it more intense, you're basically making the amplitude bigger, normally. There are other ways to make a wave more intense, but that's one way of doing it. Number 3, this is the cutoff frequency. If F is less than Fc, no electrons. We had no explanation for this. That doesn't make sense. For some reason, the electrons were completely ignoring the energy in the wave, and we just didn't know why. That just simply doesn't make sense. Just because you go below a certain value, why on earth should the electrons not make use of the energy, get excited, and leave the metal? Basically, the wave model couldn't explain that. And number 4. This is the time, almost no time delay. So what we're talking about here is if I have a piece of zinc and I have a lamp and I shine the light on the lamp, from the lamp onto the zinc, then when I turn the light on, obviously it takes a bit of time for the light to reach zinc, but almost zero because light travels pretty quick. And then electrons shoot out. And the time taken from turning the light on to shooting the electrons out was almost zero. Now, if I had a very intense light with lots of energy, then the argument was the electrons should come out really quickly because there's a lot of energy there for them to make use of. If the light was incredibly dim, almost no energy there, it should take the electrons a long time to take that energy, make use of it, and escape. But it didn't seem to. The electrons, admittedly, there was less of them, but the electrons just seemed to escape instantly. And we had no explanation for that. basically, this situation then is that the wave model, whilst being able to explain a couple of the observations of the photoelectric effect, could not explain the whole thing. And so next time we'll look at how this problem of the wave model was overcome.